In this video, I'm engineering this bike part from scratch using only FreeCAD. I'll take you through the entire process: design, full assembly, creating pro drawings for manufacturing, printing it at home, and real-world testing. I'm showing you every single step to prove what this software can really do and that it can be used by real engineers. Let me show you the process. Before starting the project, the most important step is to understand how a pedal works mechanically. It is a simple mechanism where the axle is fixed and the pedal body rotates around it. This rotation is ensured by bearings. They are composed of a cage pressed into the pedal and steel balls. At the pedal entry, the axle will press against the balls while the exit will feature a cone nut. We will also use a lock nut on this side to secure the assembly. This is the mechanism that allows the rotation. As in most engineering projects, we cannot start from scratch by creating every single part, as production costs would be excessive. Instead, we will source standard components such as the axle, caps, balls and dust guard, as well as the inserts that will be pressed into the pedal to secure the pins, ensuring the pedal's grip. Though, as you'll see later on, we're still going to have to create our own custom part to ensure better strength. We're going to start by recreating them in 3D. First, we'll take measurements of each component and transfer them onto a quick drawing, which will help us build our sketches inside FreeCAD. The parts to recreate are relatively simple. The cages and the axle are obtained through a revolution operation, which rotates a sketch around an axis. The nut will come directly from a database, while the cone nut will be slightly more complex to model, though nothing too difficult. To model all of this in FreeCAD, we will select the Part Design Workbench. This workbench provides a workflow very similar to commercial CAD software. What differs slightly is the concept of a body. It is mandatory to create one to begin modeling, as it will contain all of our features. Then, just like in any proper CAD software, we're going to create a sketch for the profile of our revolution, using the measurements we took. We'll use the polyline tool to rough out the shape, and then we'll use the dimension tool to fully constrain the sketch. We're also going to add the fillets directly into the sketch to minimize the number of design features. Next, we just need to run the revolution tool, making sure to select the correct axis, and there we go, we have our solid body. Next, we are going to create a new body for the bearing balls, and we'll position them right where they need to go. In FreeCAD, bodies operate independently. To reference the geometry of our bearing cage, we have to use a sub-shape binder. We'll project the curved face so we can center the ball perfectly inside the cage's fillet. Just select the face, click the tool, and you'll see the imported face appear in yellow. From there, we just need to generate a sphere by selecting the arc from our binder, which positions it exactly where it belongs. Then we give it the right diameter. To replicate the balls, we'll use a polar pattern, selecting the correct axis of rotation and setting the number of occurrences to 13. By making the cage visible again, we can see that the balls are perfectly in place. The beauty of this workflow is that everything is parametric. If we change a value in the cage's base sketch, the position of the balls will update automatically. And this will be highly efficient for creating our second cage, which has slightly different dimensions. To achieve this, we select both bodies, then press Ctrl-C and Ctrl-V. This will duplicate the bodies while maintaining the links between the copies. Next, we simply modify the base sketch to adapt it to our dimensions and change the number of occurrences. Since the cage is smaller, we require one less ball and the process is complete. To avoid getting lost in the tree view with all these different bodies, we're going to rename them using the F2 key. Following the same logic, we're going to create the axle. We'll start with the sketch for the revolution. I'll spare you the entire sketching process since there's nothing complicated here. The hardest part is just accurately transferring the measurements. Then we run the revolution. To make threading things on easier, I usually add a slight chamfer where the threads will go. Generally, I don't model actual threads on my parts because it can really tank software performance. I prefer to just node them on the technical drawing, but if you do want to model them, you can use the thread workbench found in the add-on manager. You just select the face, input your thread parameters, and it generates them automatically. It works for both metric and imperial. On my axle here, I have imperial threads on the crank side and metric threads on the other end. We won't bother modeling the nut ourselves. We'll generate it with the Fasteners Workbench instead. Only caveman models standard parts from scratch. If you don't have it yet, you can download the workbench from the add-on manager. Here, we just select the ISO 4034 standard and set the size to M6. Afterward, I prefer to create a part container and place the fastener inside. This groups all objects related to this nut, such as an LCS, which stands for Local Coordinate System, which will be highly useful for the assembly. For the cone nut that will rest against the balls, it is a less standard component, so we will model it ourselves. Here as well, the process is straightforward. We will create a sketch for a revolution, followed by a pocket feature to create the hexagonal shape. And we'll finish up with a small fillet on the edges to break the sharp corners. Before moving on to modeling the pedal body, there's one more part to design that I haven't mentioned yet. It's the dust cap to protect the bearings from dirt and water. Again, this is a very simple part where all we need is a sketch for the profile and a revolution to create it. Modeling the pedal body is where things get tricky. We want a look that feels super pro, but because it's meant for 3D printing, we have to design it to be easily printable with zero supports and minimize steep overhangs. You can see the different stages of prototyping right here on the screen, leading up to the final design. To model this component, we will start from a rough design and gradually refine it until we achieve this sleek finished piece. We'll start by sketching a parallelogram with a thickness of 22 mm and a length of 95 mm. Next, we'll do a symmetrical extrusion of 90 mm. This first step gives us the basic footprint of the pedal. I came up with these dimensions after several tests to see what fit my foot best. The 22 mm thickness is determined by the size of the bearing cups, ensuring we leave enough material above them. We then create a sketch on the top face, drawing a triangle on one corner to simulate a chamfer. Next, we execute a pocket feature to remove the material. To replicate this operation across all four corners, we will use a multi-transform feature, combining a mirrored symmetry and a polar pattern to generate this geometry. Next, we're going to cut all the way through the pedal. To do this, we'll create a sketch on the top face. Using the external projection tool, we'll select the face to project all of its edges onto our sketch. After converting these projected lines into construction lines, we'll select them all, use the offset tool and apply a 10 mm value. We then repeat the exact same steps on the bottom face, which gives us another sketch with a 10 mm offset. To maintain this offset all the way through the part, we'll use a subtractive loft operation, and there we go. We have our cage structure. Next, we'll draw a rectangle on the XZ plane with a width of 17 mm and the height of the pedal. Then we'll perform a symmetrical extrusion up to the face of the pedal to create the housing for the axle. The axle won't actually go all the way to the outer edge of the pedal. To increase the pedal's strength, we're going to widen the end section a bit. To do this, we'll create a sketch on the inner left face of the pedal, draw a rectangle. This time with a width of 19 mm and then perform a 31.55 mm pad operation. We're also going to add some reinforcements to further increase the pedal's strength. To do this, we'll create a sketch on the top face of the pedal. We'll project two edges so we can snap our drawing onto them. Next, we'll draw a trapezoid with a width of 8 mm, placed 3 mm away from the red axis. Once the sketch is drawn, we'll perform a pad operation up to the bottom face of the pedal. Next, we'll use a polar pattern to repeat this extrusion on the other side of the pedal, making sure to select the y-axis. And there we go. We have the rough base of our pedal. Now we're going to tackle the different pocket operations needed to fit the axle and the bearings. We'll start by creating a sketch on the right side face of the pedal. Then we will sketch two circles. The first corresponds to the axle diameter and will make it slightly larger than the axle itself. The second corresponds to the bearing housing. The bearing cup on this side has a 16.7 mm diameter. Because we require a press-fit condition, we must specify a slightly smaller diameter, 16.6 mm in this case. This provides sufficient interference for a secure fit without risking part failure during assembly. We will then select the inner circle and execute a through-all pocket feature to completely pierce the pedal. Afterwards, select the outer circle and perform a pocket operation over a distance of 8.3 mm. Now we'll move to the other side of the pedal to create the pocket for the second bearing cup. By selecting the face and creating a new sketch, we'll once again set a diameter slightly smaller than the cup for the press fit, which will be 15.9 mm. Next, we'll perform a pocket operation with a depth of 41.5 mm. This depth is somewhat arbitrary for now, as it will be determined later during the axle assembly. In the tree view, I'm going to rename it Pocket X so I can easily find it later, since it's bound to change depending on the assembly. The next step is adding the fillets. This is a super important phase because these fillets will completely transform the part, giving it a smoother, less sharp look. More importantly, they're going to drastically increase its strength by smoothing out stress concentrations that could otherwise cause the pedal to snap. Now we're going to add a few chamfers to make the pedal look a bit less boring. We'll apply them to both the inner and outer contours. One of the final steps is adding the slots for the threaded inserts where the grip pins will be screwed in. To do this, we'll create a sketch on the top face and position all the holes. I'll skip the sketching process itself since it's quite time-consuming and not very complex. Next, we'll perform a pocket operation with a depth of 4.1 mm. Then, to replicate these holes on the other side of the pedal, we'll just use a polar pattern around the y-axis. To put the cherry on top, we will add a small fillet at the junctions of the chamfers to blend everything smoothly, and our component is finished. We are now ready to proceed with the assembly. Prior to this, some preparation is required on the components. We will attach a local coordinate system to the specific locations where the parts will interface. Although somewhat time-consuming, this step is essential to ensure a highly robust assembly that won't break during future modifications. Before that, we're going to create a part object to group the bearing components, specifically the cage and the balls. This will make them much easier to handle later on, especially since these parts stay fixed relative to each other. We need to do the exact same thing for the second bearing at the outer end of the pedal. Just create its own part container and drag and drop the two bodies inside. Now we're going to create the LCS that will be used for our assembly. Before starting, make sure the object you want to create the LCS on is active. Here we're going to create the attachment points for the first bearing, so right-click and make sure to select Active Body. Next, select the edge where you want the attachment point to be and click the Coordinate System tool on the right. Since the edge we selected is a circle, the object will be created concentrically right at the center. This is exactly what we want, so we can go ahead and accept the placement. We are going to create another one where the balls are, to give us an attachment point for the axle. Let's select the edge right between the balls and create another coordinate system. Now we need to do this for all the remaining parts. However, I want to draw your attention to the pedal body itself. Since we have quite a few fillets on this body, it can be a bit unstable. To handle this, we're going to create our coordinate systems before applying those fillets. To roll back the history in the tree view, simply right-click on the operation you want to go back to and click Set Tip. From this point on, any action you perform will be inserted right after that operation. This is incredibly useful here because it allows you to rely on much more stable geometry rather than working post-fillet. So here are all the parts we'll be using for the assembly, each with their respective coordinate systems that will serve as attachment points. Just so you know, I do it this way to prevent any errors, but you're not forced to do it at all. The assembly workbench can handle this automatically. However, this solution is much more stable. To keep the file well organized, we're going to create a parts group and drag and drop all our pieces inside. This will allow us to clearly separate the source parts from the assembly itself. We can then switch to the assembly workbench and initialize the assembly object. We're going to create a fixed assembly. Even though the pedal rotates around the axle, there's no need to make a dynamic assembly here. Let's click on Components on the right and import all our parts. To simplify the process, we'll start by importing the piece that will remain fixed. In this case, we'll choose the pedal body. Then we can import the other parts just by clicking on them. Using the gizmo, I usually like to pre-orient the parts so they're already in the right position, but you don't strictly have to do this. We will exclusively utilize the fixed joint for this assembly. Here we're going to constrain the cage to the pedal body. We'll click the tool and then within the viewport, directly select the LCS we wish to constrain to each other. The cage will then snap right into its precise housing inside the pedal, which is exactly what we want. We're going to repeat this process until the entire pedal assembly is complete. To get a better view of what's going on, I set the pedal's transparency to 80. Here we can see that the axle is too short and the cage is too far out. We're going to adjust the pedal so everything fits better. In the tree view, let's go into the pedal body and change the value of pocket X, the one where I mentioned I had put an arbitrary value so we could adjust it later during the assembly. Using the gizmo, I'm going to increase the value up to 47 mm so that we have enough thread for the nuts. But with this value, as you can see, there's very little plastic left and the contact with the axle will only cover barely half of the pedal, which is far from ideal. So we're going to modify the axle directly within the assembly to get it to the right dimensions. This implies that we won't be able to use a standard off-the-shelf axle and we'll have to machine our own instead. So we're going to head over to the tree view, go into the axle body and modify the revolution sketch. We'll give it new values to make the axle longer and we'll increase the distance between each shoulder to keep the part uniform and solid. Now we can see that the axle is longer, but the cage placement is completely off. We need to change the value of pocket X in the pedal body again. This time we're going to set it to 24.5. Once we accept the operation, the model will regenerate, and we can now see that both the axle and the cage are properly positioned. For the machining of this axle, we will be relying on PCBWay, the sponsor for this project. They are simply leaders in PCB manufacturing, 3D printing, and CNC machining. To have them machine the axle, we first need to upload the file, and we can do that directly using the plugin inside the software. This will open up a web browser and upload the file automatically. Given that this requires CNC machining, let's navigate to the Machining tab. We will then set the quantity to 1 to generate a preliminary cost estimate. There is a wide variety of materials to choose from. For this application, a high-strength metal is critical to withstand both the rider's weight and trail impacts. Therefore, we will select 4140 alloy steel and add a nickel plating surface treatment to provide long-term corrosion resistance. If we stick to these settings, PCBWay will machine the part, but won't add the threads. To get that done, we need to create a technical drawing showing the location, thread dimensions, and tolerances. Let me show you how to easily make this drawing right inside FreeCAD. The first thing we're going to do is head over to the TechDraw workbench. Then we'll create a new drawing page and load a template. I'm choosing the A4 minimal format here, but you have plenty of other options available. Now we're going to import our axle. To do that, make sure you select the axle in the tree view, then click on Insert View. This opens up a panel on the right where you can choose your view orientation. Right now we're looking at the axle from the front. To get the side view, just click on the right arrow. The axle looks a bit small on the sheet, so we're also going to double the scale before creating the view. Now you can add the different dimensions, but since we already sent the 3D file, the most important thing to annotate here is the threads. We're going to add visual lines on the axle to show exactly where the thread is supposed to end. To do this, we'll draw some cosmetic lines. We can use the existing points on the drawing and then create a line between them. In the panel on the right, we're going to translate the position by the exact thread length we want. We need to do this for both points. After hitting apply, a dashed line will appear on the drawing. We'll just double click on it and change the style to a solid line. Next, using the dimension tool, we'll add a horizontal dimension between the far edge and the line we just drew. This distance will define our thread length. Then all we have to do is repeat the exact same process for the crankside thread by creating another offset line and adding the horizontal dimension. Now we're going to add a cosmetic arrow to point to the thread. To do this, we'll use the leader line tool. To draw the line, we just click on pick point and then place our points on the drawing to form an arrow. After that, we just click save point and accept the operation. We will then utilize the annotation tool to specify the thread parameters. First, we will indicate the nominal size, which is M6. Next is the pitch, which is 0.75 in our case, followed by 6G for the tolerance class and 14 representing the total thread length. After that, we can simply drag the annotation to our desired location. While we're on the subject of threads, let me explain how I figured out the thread pitch. I actually want to reuse the same nuts on this new part. To determine the pitch, I took a picture of the original axle, then I imported a photo, scaled it correctly using the ruler as a reference, and counted 10 crests, which I then divided by 9 to obtain the pitch. Just a little pro tip for your future projects. Back on our drawing, we're going to do the exact same thing for the crankside thread, starting with a leader line and placing our 2 points. Then we'll create another annotation, but this one will be in imperial. 9/16 for the nominal diameter, 20 for the threads per inch, U and F for the fine pitch series, 2A for the tolerance class, RH for the right-hand thread direction, and 10.25 for the thread length. Next, position the annotation correctly, then update the drawing title block. Set the scale to 2:1, change the material to alloy steel 4140, and update the document number and part name. So far, we've created the drawing for the right pedal. However, the left pedal uses a left-hand thread, so the drawing needs to be updated accordingly. Since we're not cavemen, we're not going to recreate the drawing from scratch. Instead, go to the tree view and copy the page we just created. When the copy dialog appears, make sure to select only the objects related to the drawing, the page, the template, and all the annotations. Next, paste the copy into the tree view. A duplicate will appear, which we can rename to axle left. Then update the thread designation by changing it to LH for a left-hand thread, and don't forget to update the part name in the title block. Now that everything is ready, all that's left to do is right-click on the sheet to export it as a PDF and send it over to PCBWay for manufacturing. A few days later, I received a photo from PCBWay for a final visual inspection before the parts were shipped. And now here we are with the package. Thanks to their professional service, just as they say, they turned my design into reality. There are several other parts in the box that we'll look at later, but for now, we're interested in the axle. As you can see, it's extremely well packaged. It also comes with an inspection report confirming the critical dimensions and the thread specifications. And as you can see, the part looks perfect. The whole axle part was just a little side quest boss like Malenia in Elden Ring. The main objective here is to create the actual pedal body. I want to print this cage at home on my KiDi Plus 4. However, I want to benchmark this print against a professional selective laser sintering process, which delivers superior mechanical properties and surface finish. For my print, I'm going to use a 15% carbon fiber reinforced nylon, which was kindly provided to me by Polymaker. It's one of the best filaments for this project because it has excellent mechanical strength and is less sensitive to moisture. Even though, as you can see here, it still needs a good drying session before you can use it. While FDM printers are highly capable, dimensional inaccuracies frequently occur between the CAD model and the printed object. According to the datasheet of this nylon, the shrinkage rate is acceptable for the X, Y, and Z linear dimensions. However, diameters show a noticeable variance. Consequently, we will need to either apply a global scale factor to the part or compensate by expanding the diameter tolerances. This pedal design involves several critical dimensions, specifically the diameters for the bearings and the threaded inserts. Because these components are press-fit, the holes must be slightly undersized to ensure a tight hold. However, we must be careful not to make them too tight, as excessive hoop stress could crack the pedal body. To avoid wasting filament, I modeled this test piece that includes all the critical diameters and holes, the 2 diameters for the bearings, as well as the holes for the inserts. I need to print this part in the exact same orientation as the final design to make sure we're in the same configurations. Before launching the print, the filament absolutely needs to be bone dry. I used Polymaker's dryer to bring the humidity levels down to 10%, and I'm using active drying throughout the whole printing process. After running several tests, I decided to make the diameters 0.1 mm larger to get a perfect press fit. I highly recommend using this technique. If you are working on large parts with tight tolerances, it's going to save you a ton of material. Regarding the slicing parameters, I'm relying on the stock Polymaker profile for this material. In the quality settings, I modified the wall generator from Classic to Arachne to optimize perimeters and line width. In the Strength tab, I adjusted the wall loops to 8 to achieve a solid perimeter thickness exceeding 3 mm. I configured both the top and bottom shell thickness to 3 mm as well. To maximize mechanical resistance, I selected the gyroid infill pattern with a 30% density. The objective is to maintain a uniform 3 mm nylon shell across the pedal body. Printing a fully solid part is unnecessary, as maximum thickness is only critical in high-stress zones. I also added an outer brim around the pedal to increase bed adhesion and minimize any potential warping. Using the Preview tab, I then check to make sure there are no areas where the wall thickness is too thin. This is the final verification step before launching the print. And off we go for a 4-hour print. While we wait, let's switch focus to the SLS version handled by PCBWay and upload the pedal body directly from the add-on just like we did for the axle. Unlike the FDM version, we're going to choose glass fiber reinforced nylon. Out of the 3 nylons offered here, this one will provide the best long-term mechanical strength. We could also ask them to install the inserts for us, but just like for the axle threads, we need a technical drawing. Let me show you how I made it in FreeCAD. The first thing we're going to do is generate the inserts. To do that, we'll head over to the Fasteners Workbench. I'm going to create a part to group all the inserts that go on the top face of the pedal. Then, by selecting all the whole edges, I'll just click on the insert icon to generate them all at once. In the tree view, I'm going to select all the inserts and change their size to M5, set the outer diameter to 5 mm and the length to 4 mm. Then I'll just drag and drop them into the insert's top part. Next, I'm going to repeat the exact same process for the inserts on the bottom face. Another trick would have been to generate a single insert and place them one by one in the assembly. That would be cleaner, but much slower. Grouping the top face and bottom face inserts separately like this makes it super easy to constrain them all and easily create the exploded view later on. I'll then move these 2 parts into my parts folder to keep the file clean. Next, I'm going to add them to my assembly. To do this, I'll start by hiding all the other parts and making the assembly visible. Then I'll double-click it to make it active, import the inserts into the assembly and use a fixed joint to place them. I'll do the exact same thing for the bottom face inserts. My goal is to create an exploded view of the assembly to show the position of each part and how they fit together. We'll start by using the Exploded View tool. Using the navigation cube, I'll switch to an isometric view, then move each component according to its assembly direction. For instance, since the inserts are installed vertically, I'll move them that way, while other parts will be moved horizontally. Make sure to place everything carefully, as this is the exact layout we'll use on our technical drawing. I also want to generate a bill of materials to include in my drawing. To do that, I just need to click on the Bill of Materials tool and my list will be automatically created. Next, I'll head over to the TechDraw workbench and create a new sheet, choosing an A3 template to give us plenty of space. To insert my exploded view, I first need to select it in the tree view and then click the New View tool. I'll click on the bottom right box to generate my isometric view. Since I don't need the side view, I can just hide it in the tree view and then reposition my isometric view on the sheet. To prevent it from moving during a recompute, I can check the lock position box. Now I'm going to import my parts list. To do that, I'll select the Bill of Materials spreadsheet, and then from the TechDraw menu, I'll use the Spreadsheet View option. To see the cells I need, I just have to change the range in the left menu and select up to cell B10. This is what allows us to display the complete list inside the table on our sheet. Then I'll call out each component using the Balloon Annotation tool. Each item balloon will display a specific number that matches its index in the bill of materials. The final step will be to create an annotation for the insert dimensions. In this case, it's 20 inserts for M4 screws with a length of 4 mm and an outer diameter of 5 mm. I'll also add an assembly note specifying that the inserts must be flush with the pedal surface. Before sending it off, we just need to update the title block of the drawing and we'll be good to go. Meanwhile, our in-house 3D printed pedal body is complete. We can now compare it with the SLS parts manufactured by PCBWay and proceed with the final assembly. Just like with the axle, the cage arrived extremely well packaged. You can really see the exceptional quality of this pedal. It feels like a true finished product, not just a 3D print. They did a great job installing the gold threaded inserts, and the final look is absolutely fantastic. After installing the inserts in my homemade version using the right tool for the job, we can now compare the two pedals. Both are exceptional, and you could easily believe they are injection molded plastic rather than just 3D prints. Honestly, the FDM version is the biggest surprise here. I have never achieved such a clean print before. My KD4 Plus is an incredible machine, and using carbon fiber infused filament works wonders to mask the layer lines. While the tolerances and diameters aren't 100% perfect, they are highly acceptable. The only minor issue is the first layer that was in contact with the build plate. Other than that, the result is outstanding. And what can I say about the SLS version? It's simply extraordinary. Of course, the manufacturing process is different, but you can really feel the quality and sturdiness. All the small fillets and chamfers came out beautifully and the dimensions are absolutely perfect. In terms of mass, the SLS version is 28 grams heavier. This difference is explained by the 30% infill used on the FDM print. Regardless, it remains an extremely competitive weight. Now let's move on to the assembly. The first step is to press the bearing caps into the pedal body. To make the press fit easier, we'll use a little grease, and once again, using the right tool for the job, we'll press the caps in. We repeat the same process for the cap on the other side, but this time it has to go deeper. We need to be careful to keep it perfectly straight. Next, we add some more grease, this time for the bearings. It's really important if you want to avoid any annoying squeaks or noises. Next, we need to put the dust cap on the axle. This is what's going to protect the bearings from any dirt and debris that could get inside. Then we slide the axle into the pedal. To be able to insert the bearings, we have to pull it back slightly and then we can drop in our 13 loose balls. Once that's done, we can test the assembly to ensure the axle rotates smoothly on the bearing balls. Next, to install the bearings on the opposite side, we must flip the pedal and rest it vertically on its axle. On this side, we add the 12 bearing balls, and then using a small 3D printed tool, we screw in the cone-shaped M6 screw to ensure the bearing functions properly. We must be careful not to over-tighten, as this will bind the pedal. Conversely, under-tightening will introduce play. This is precisely why we use a fine-pitch thread on this axle. And as you can see, the adjustment is spot on. There is no play and the pedal rotates freely. All that's left is to add the lock nut to fully secure the assembly, then install the pins for grip and the pedal will be completely assembled. As you can tell, the result is flawless. The pedal looks incredibly professional and the bearings work beautifully. It spins just like a fidget spinner back in 2017. What's going to be really interesting now is seeing how well it holds up in real-world use. On one side I'll have the SLS pedal and on the other the FDM one. I started off by doing a quick bunny hop in my backyard and they didn't budge. Then I took them to a mellow local spot with a few jumps and manuals, and same thing, they held up perfectly. Following a careful post-ride inspection, both pedals showed no signs of structural fatigue or significant impact. I only lost a couple of grip pins along the way, which can easily be fixed by using some thread locker next time. But the most important takeaway from this video isn't the pedal itself, it's the entire manufacturing process. As the saying goes, it's not about the destination, but the journey that got us here. We saw that with a free open source software like FreeCAD, we could reverse engineer parts, design a product, build an assembly, modify it on the fly, and generate technical drawings to send to a manufacturer. It's a real engineering project, worthy of a professional design office. And the best part? I've only shown you a fraction of what FreeCAD can do. I hope I've managed to change your mind about this software and that you'll consider adding it to your workflow. If you want to learn it, I have plenty of tutorials on my channel, and I highly recommend starting with the STEM video to get all the basics down. Thank you so much for watching all the way through, and I'd also like to take a moment to thank the amazing channel members you see on the screen right now. If you enjoyed the video, don't forget to like and subscribe. Thanks for watching.